All right, good afternoon, good day, or good night, depending on whenever you're watching this. Right, this is Mr. Fred, and welcome to your recap session for transfer processes. As I have already highlighted that I was going to send this to you, and then you can have a look at some of the things that you really need to pay attention to as you are preparing for your test 3, right? Okay, so this session is going to be short and brief and straight to the point. So we'll be looking at mainly 5 things here. Number one, we need to recap on your approach to transfer problems, whether it's mass transfer or e-transfer. Number two, we'll then look at the key concepts and models in which you approach your questions. And then thirdly, we'll look at some of the common mistakes that people were making when it comes to test one and test two, and as well as your engineering judgment, because remember, a lot of things that you calculate are related to a specific conclusion that you need to make after finding out your values. And then lastly, how you're going to be preparing for your test 3, just to make sure that you're well aligned. So number one, how to identify the governing mechanism. How to identify the governing mechanism. All right, so this simply means context, the word which has turned out to be our favorite word for the semester, for the most part of it, when we are reaching towards the end. So one, you know that you are going to have conduction, and you know that has to do with the Fourier's law, right? So Q is equals to Ka dt over dx or dy, right? And mostly, whenever you are having your heat transfer calculations, you won't find us saying calculate conduction and then you go and use the Fourier's law, right? Unless you're asked to find things like the values of K, that's when you can now go back to the Fourier's law as it is. But mostly when you find conduction, it will be in this form of saying Q of conduction is equals to Q of convection plus Q of radiation, right? So you know that once you have the Q of convection plus the Q of radiation, you can sum them up to get the Q of conduction, right? So there are some of the things that when you are actually reading the problem statement will give you an idea that actually here I need to find the Q of convection and the Q of radiation and then sum them up to get the Q of conduction. You will see that for whenever you're dealing with convection, you will be given some velocities as well. And if you are dealing with the radiation as well, we might tell you to assume gray bodies or black bodies or whatever kind of a body. So those kind of things will suggest to you and give you an idea of the context that we are working with, right? So always pay attention to that, right? So it will mostly be like this. Whenever we ask you for Q of conduction, you would go and find Q of convection and add it to Q of radiation, right? So that is the first thing that I want you to look at. And secondly, simply means that for convection and radiation, you already know the steps for that, but we'll go through them just now. All right, so you need to find out conduction, convection, radiation, diffusion, and the mass transfer coefficients, right? And then radiation, you need to know which equations are governing these things, and you need to be able to pick up if it's the actual thing that is happening in your problem statement. So you need to ask yourself that what clues in the equation tell me which one of these is, all right? Two, I'm just mentioning this one just for control, how to choose the correct geometry. This is choosing the correct geometry. I'm just mentioning this one in passing because I've seen that some people, they're told it's a cylinder, but they force and use the area of a sphere, maybe because that is the one that they know. But because remember, there are no gimmicks and tricks from my side and from yours, right? So it simply means that we won't be awarding marks for those kind of for that kind of creativity. All right. So you need to understand the formulas for plane walls, for cylinders, and for spheres. So plane, or it's a flat plane, a flat plate. You need to look at the cylinder and sphere. And for what? All of these, they can either be external or internal. So you need to find out when it's flowing in a cylinder or a sphere, on its outside or on its inside, what are the actual formulas that you're going to use? So you need to be well aligned with those. All right. And then 3 units and physical meaning, units conversion. I think we are fine now. Right. And then before we do anything else, your engineering judgment. Is the design acceptable? When you are told that the limit is this much, you find the value to be below or greater than that. You need to be somebody who is actually able to say the design is acceptable based on the fact that it's lower or greater than the design limit, depending on whatever that you see. Is the cooling adequate? If we say that we need to be cooling by removing 5,000 kilojoules, right, per second, you need to be somebody who is able to say, my value was below that, therefore the cooling is inadequate, or my value was above that, therefore the cooling is adequate. Is the insulation possible? Not really possible, but is the insulation suitable? Yes, that's the word. Right? If you see that you have insulated, but you are still taking out more heat even with that insulation layer after calculating your thermal resistance, then you can comment and say the insulation is not suitable. And then lastly, what recommendations can you make then for this case if it's not suitable, or if it's not acceptable, or if it's not adequate? So you need to be somebody who is well equipped for those scenarios, because everything that you answer is linked to an engineering judgment. Right. Okay. So I think that's it for the brief of what to expect. All right. And then from here, I think we can then just go to common mistakes people have been making in their test 1 and 2. Test 1 mistakes. Mistake number 1. Temperature to linearly interpolate fluid properties. This has been a huge one, and we're going to talk about it just now. So the temperature at which people interpolate the fluid properties at, and which temperature you're going to use as your delta T. Those have been some of the mistakes, and then we can just jump straight to it then and start talking about those and how to actually go about it. Here we are. Then let's talk about the temperature now. Right? You've got the film temperature, which will be the temperature at which you interpolate the properties of your fluid sometimes, but as well as Tm. Right? So let's start with case 1. When you have got a fluid that is flowing or on a flat plate, whether it's air around a flat plate or so, your T film is just your surface temperature plus the temperature of the fluid at an infinite distance from the surface, so that is temperature, or T infinity, all divided by 2. Then this becomes your TF. And then for a temperature difference, if you were to go to your formula on the delta T, you will just put your TS minus T infinity. This is very simple and basic, and mostly applied to when you are dealing with flat plates. Right? Case number 2. You've got a fluid that is entering a pipe and leaving on the other side. The value that you will be interpolating the fluid properties at, let's say the fluid properties that you are going to be using for your Reynolds number calculations, this is what we are doing. You are going to say Tm is going to be the temperature in plus the outlet temperature, all divided by 2. All right. But for your delta T on the formula, you can see the formula here at the bottom. the delta T that you use is going to be the log mean temperature difference, right? I see here what I have on the picture is saying Q is equal to UA delta TLM, right? That is using the overall heat transfer coefficient. But for us, we'll be using what we have been using for conduction, convection, and radiation. Just give you an idea that your delta TLM is what you'll be using whenever you are dealing with the case of a fluid that is flowing inside a pipe, right? Okay, case number 3. You have got a cylinder or a sphere that is in cross flow of a flowing fluid. Let's say air is approaching at a temperature of 50 degrees. The surface is at a temperature of 100 degrees. And then by the time the air passes, this is now at 70 degrees. Which temperature are you going to use to evaluate the properties of the fluid? You are going to use the film temperature. But the film temperature for this case is a bit different based on the term for T infinity. This is T infinity here. Temperature of the fluid at an infinite distance from the surface. So you can see that it generally still says T infinity plus Ts over 2. But your T infinity now is T in plus T out over 2. Alright? So that is just what you would use. I hope that is clear on this case, and then we can just move to something else. Now we are here. The second most common mistake that people have been making: when to use the cross-sectional area or the total surface area. Right? So this all depends on how your phenomena is interacting with you, whatever boundary that you have. Right? It might be an opening of a pipe. It might be from the other surface to the other surface of a flat plate. But let's just look at it. If something is moving through the area, water flowing inside a pipe that's flowing through the area or moving through the area, you are going to be using the cross-sectional area for that. So it simply means that for your calculations of Reynolds number and stuff like that, right? So for Reynolds number, when the fluid is flowing on the inside of a pipe, we are going to use the internal diameter, right? But for the Reynolds number, when the fluid is flowing externally, we are going to use the overall outer diameter, right? So you can use this for calculations of volumetric flow rate through the area, mass flow rate through the area. The area for this is always cross-sectional. Or conduction heat through the wall, right? From the other side of the wall to the other side of the wall, right? And any flux, whenever you're dealing with mass, heat, and momentum that is passing from the other side of the wall through the thickness of the wall and then out on the other side. I hope this makes sense, that you're going to be using cross-sectional area in such cases. So there's no way that you'll use the total surface area to calculate the Reynolds number, right? So this will always be the cross-sectional area. But then, when the phenomenon now is acting on the area, right? So let's say you've got something inside the pipe and is diffusing through the pipe walls to the outside. That becomes the total surface area that is available, all right? So it simply means that for your rate, whether it's mass transfer rate or something that is acting on an area, normally is going to be the total surface area, right? So for convective heat transfer, total surface area; radiation heat transfer, total surface area of the sphere, the cylinder, of the flat plate; and then mass transfer, the surface, you're also going to be using that kind of area. And there are other things that people use the total surface area for. But bear in mind that unique cases can occur that you are using the cross-sectional area to calculate the rate. Let's say I've got a tank, a vertical tank, just like you had in your question 2. It contains water here, and water is diffusing through molecular diffusion throughout the top. The only area that is available is just that opening at the top, which becomes the cross-sectional area. I hope that makes sense on how that material transfer is happening. So these are just some of the issues that people had in their test 1 and test 2. So I think by doing that, we would have covered that. So we talked about your temperature difference that you use, as well as the temperatures of the fluid to say where do you interpolate at. and as well as areas. Cross-sectional area or area cross-sectional, and area, which is your surface area. Okay. We said that whatever that you do here is linked to an engineering judgment, right? It's linked to an engineering judgment. For example, let's look at your question 3 that you had for test 1 before we move, all right? So in test 1, we said that following a technical assessment, you are presented with a follow-up engineering task to evaluate your suitability for the Junior Thermal Systems Engineer role at Thermacore Systems Ltd. So that is the company. So now you are investigating the thermal conductivity of a new type of rubber that is intended for use as cooling water housing, right, in an engine system. And then for this purpose, you are given a spherical test section that you are going to use with an inner diameter of 0.2 meters. Spherical test section. This is what they are giving you. The diameter, di of this, is equal to 0.2 meters. And do of this is 0.24 meters. And then they say that a heat flow of 100 watt is applied uniformly to the inner surface of the spherical body. So the Q that is being added is 100 watt or 100 joules per second. You apply this uniformly to the inner surface of the spherical body, resulting in a measured temperature difference of 100 Kelvin between the inner and the outer. So if you can draw this is a sphere, right? The temperature dt is equals to 100 Kelvin between the inner and the outer. The outer diameter is equals to 0.24, and then the inner diameter is 0.2 meters. Then the question comes and say, estimate the thermal conductivity of the rubber. You are supposed to estimate the thermal conductivity of the rubber. So let me just add something. Let's say the engineers want this rubber to have a thermal conductivity of 0.2. Watt per meter per Kelvin. So your role now becomes to determine whether this kind of material will be suitable for what they want to do. So you need to find the thermal conductivity and compare it with what is being required. So what I'm going to do, we're just going to say that this is a Q of conduction, right? So this is a Q of conduction. It's a small q, just like we've always been mentioning that the big one will always be the flux. So we're just going to say that my inner radius is equal to 0.2 meters. You divide that by 2, you get your 0.1 meters for your inner radius. Your outer radius is equal to 0.24 meters. You divide that by 2, you get 0.12 meters. If I'm making any mistakes here, you can amend them on your side. But then you know that Q of conduction is equal to T of the surface inner minus T of the surface outer divided by R, which is your thermal resistance. So, and then you know that your R is equals to TSI, T of the surface inner minus T of the surface out, divided by Q of conduction. You just rearrange. And then now you've got 100 for the temperature difference is given. It's given. Divided by the 100 watt is given. And then it gives you 1 Kelvin per watt. This is what you found as your R. But remember, you're looking for K. And you know that R is equal to This for a sphere, 1 over Ri minus 1 over Ro divided by 4 pi k. And then at this stage, what do? You rearrange again so that you can have it in a form of k as the subject of the formula. Then 1 over Ri minus 1 over Ro divided by 4 pi k. That's my mistake, 4 pi r instead. Then you just substitute what you have, 1 over 0.1 minus 1 over 0.12 divided by 4 pi multiplied by 1. And the answer that you should get, it should be 0.133 watt per meter per Kelvin. And then remember, the engineer said the specifications need to be at least 0.2 watt per meter per Kelvin. Then now your question becomes, when I compare this, does it meet the spec by the engineers? No. Therefore, the material is not suitable because what? The 0.2 or the 0.133 is less than the 0.2. And then you can write even your other creative reasons for that. All right? Because there will be a mark for this statement that shows your engineering judgment. Okay. So that is that. Just trying to give an idea that you'll always be required to do some form of, or to have some form of conclusion for what you find. All right? So this was just a demonstration of this. Of what I was trying to show. I think now you have your test one, you can go through it and actually see where you went wrong. For most of you, we have spoken about that, right? But then now just look at your question 3 from test 2. Okay, so I think this will generally be the last thing that we look at in this recap session, because the main aim is not to reteach, but to actually make you aware of some of the important things that you need to be well aligned with. Right, so now we are going to your question 3 from test 2. A lot of people, when they read the problem statement, it was a bit confusing for them because they didn't know how to set the context or how to find out the context of what they are dealing with, right? Let's just think about it for a second, even without reading the problem statement. I hope that you have it on the side. This is a pipeline. And inside the pipeline, we have got a fluid that is flowing. Let me just do the velocity profile. Right. So when that fluid is flowing inside the pipeline, there is concentration in bulk of A in the bulk flowing fluid. But there is also the concentration Ca, let me just say concentration of surface inner. Concentration of A on the inner surface. And on the outer surface, there is also concentration surface outer, concentration of A on the outer surface of the pipe. And then outside here in the surrounding, there is also concentration of A in the surrounding. Right? So the way these things move, you can see it now that it moves from the inside to the inner surface, from the inner surface to the outer surface, from the outer surface to the surrounding. So now let's just rewrite it. Concentration of B in the bulk, concentration of A in the bulk, concentration on the inner surface, concentration on the outer surface, concentration of A in the surrounding. I know I'm using my own notation, but if you prefer a different notation, you just need to make sure that you show us what your notation is before you continue and answer the question. So if you can look at this, the movement of A from the bulk flowing fluid to the inner surface, which process does that happen with, or does that happen through? Think about it. You'll be right if you said that it happens through internal convective mass transfer, right? That is the actual process there, where you'll have, let me use the small n for the rate. This is just going to be internal convective mass transfer coefficient multiplied by the area, and you ask yourself, is it the cross-sectional area or the total area? Then multiplied by C in the bulk minus C on the surface inner. Right? This you'll find through correlation, the HMI. The area is the total area, 2 pi RL. Right? CB is the concentration in the bulk. Normally you will be given. They will say the concentration in the bulk is just going to be equal to whatever pressure that you have, P over RT if you're assuming ideal gas behavior. Same here, P over RT, depending on what you are given. But for test 3, this is what it had to be. All right? That is just all around that process. Because the main thing, once you have got the concentration, the main thing, you just need to find the HMI. If we ask you to say, find the internal convective mass transfer rate, you just need to find the internal convective mass transfer coefficient. So it simply means that you need to find your Reynolds number, you find your Schmidt number, you choose the correlation, the correct one, please. After choosing the correlation, you find the Sherwood number. After finding the Sherwood number, you find the HM. After finding the HM, you come back and substitute. And then voila, we are passing with the distinction. Right? So these steps remain the same, nothing changes there. But then we move to the second process that is happening. Because remember, right now we just looked at when it to move from the bulk, the rate for when it to move from the bulk into the inner surface. Now we are looking at the next process, when it moves from the inner surface to the outer surface of the pipe. And which process is happening there? This is molecular diffusion. I hope we are together on this. So this one now happens through molecular diffusion. So molecular diffusion, you know, it just takes you back to the Fick's law, right? Why am I using Q? N. If it's a big N, it's just going to be the AB, the bigger, the AB, the CA over dy. You can just go with the integrated form of that, or this one, right? So what you are going to do here, you can go the Rm path, right? So you have your concentrations on the inner and on the outer side. You can still use P over RT provided that you are given the partial pressures. The DAB will always be given because we are not giving any data for that. We just give you the values as they are. The diffusion path, you have to find a way to find it, but in this case, it's just the total distance between the inner surface and the outer surface, which is simply the thickness, plus whatever layer is there. So everything combined from the inside to the outside, right? And then you do CA, that's when you find your concentration using your P over RT. If that is not working, then we can go the RM route, right? You know, just like we did for heat, the RM remains, right? But you need to use the RM for the correct geometry. If this is a cylinder, then you need to use RM for a cylinder after finding the RM, and then you can find your actual rate, which is your NA, right? And which area you're going to use here is still going to be your total area, because this diffusion or this molecular diffusion is happening through all the surface that is available of the pipe. All right, and then the third process, from the surface to the outer surface, to the surrounding, sorry about that. So from the outer surface to the surrounding, this one is going to happen through external convection. Or external convective mass transfer. And the formula for this remains. NA is just your HMO, which means your mass transfer coefficient for external convection, and then the area C on the surface, outer, minus surface in the surrounding. And then you just need to find now HM. So external convection, the driving force will be the flowing air. There will be some air that is flowing on the surfaces, not on the surface rather, but around or in the surrounding, which still makes it the air that is flowing on the surface of the pipe, right? So the way forward in this, the area is still going to be the whole area that we have, since the whole pipe is exposed to the air. But the steps are the same: Reynolds number, Schmidt number, correlation, Sherwood number, and then HM. After that, you come and substitute, and then you go. But one thing for sure, or one mistake that you should really avoid, is thinking that things always come like this. Whenever you have a process that is happening, if it involves convection or any type of mass transfer, you need to be able to pick. Is it, for example, A, or is it B, or is it C? And then you move using the correct equations that you must use. I hope that is clear, because for some people it becomes a tough thing to operate at. Okay, so lastly, I want to talk about the engineering judgment that has to do with economics. We tell you it costs this much per carbon release in the form of carbon tax, and then you need to calculate and make an engineering judgment. All right, so whenever you've got cases like those, you just need to use your conversion factors and convert what you have. If you have got mole per second and you are given that in kgs, or rent per kgs is this much, then you need to move from moles to kgs and then move from those kgs to rands using the provided conversion factor. And then you make an engineering judgment. So one of the things that people have been making real mistakes at is, people just focus more on the mathematical side of the solving of a problem, and then they forget what it means. Whatever that you find, you need to be able to interpret. You need to be able to tell us what it means, and don't just write one line. Be convincing, right? If you want to be creative, but be convincing, right? At this stage, there's not much to say. I think everything else that was left out is something that people can be able to figure out and work through over the weekend or so as they are preparing for their test 3, right? But most of the common mistakes that we experience with people here, I think we should be fine, right? I think we should be fine by now, right? Just make sure that your conversions are fine in terms of units, because that's where some people have been making mistakes. But as well as the use of absolute pressure. Whenever you're given pressure as gauge pressure, at this point you don't even have to over-explain it. We just need to say that there's no way you'll be using gauge pressure as it is. Whenever you are given gauge pressure here in all our calculations, just add the atmospheric pressure and bring it back to the atmospheric, to the absolute pressure. I think that is the rule of thumb, right? At this stage, it's the final leg of the semester or end of the module. So if you just do that, I think we should be fine. All right. And I think generally just that is just all of it. There's nothing much to say besides saying that if there's any formula that you think you might need and that you think is not provided, you have to bring it into the test. Not written on a paper, but in your head, right? In your brain. You need to embed it in your brain and bring it to the assessment venue. All right. That was just it from me. And all the best forward with your preparations for test 3. Go through test 1, go through test 2. And one more thing, most importantly, is you are not always going to be solving forward. It's possible that you might be solving backward. you don't always have to look for the rate. I can give you the rate and ask you for the temperature. I can give you something that typically you think is what we'll be asking you, but I can give you that and actually be asking you for something else. We can ask you for the length with everything that's provided. We can ask you for the temperature. We can ask you for the DAB. So always be ready for something like that. All right. Yeah, that's just it for me. And it's a Friday, hey. And as you're working through it, try to have some rest in between to make sure that you don't you don't burn out, right? So but for me, that's just it. All the best with your assessment. I will see you on Monday when you write your final assessment. Bye.